All right, so we're in the last section of chapter 9, 9.5. We're dealing with linear equations here. In particular, we're dealing with a method for solving first-order linear differential equations. This is probably the most powerful method that we're going to talk about because it will handle any linear differential equation. Of course, we need to give a definition of what it means for a DE to be linear. So if you have a first-order differential equation, we say that it's linear if you can put it in this form. dy dx plus p of xy equals q of x. So what we're thinking of here, this p of x and this q of x, I guess I should say more this p of x, we're thinking of that p of x as like a coefficient on that y right there. Now in algebra, coefficients have to be constants, but in differential equations, they can be functions of your independent variable, just so long as there's none of the y's showing up in that function, okay? So here's an example of a differential equation, a linear differential equation. Oh, and I forgot to mention this. The functions p and q are assumed to be continuous on some interval. That's an important condition, but we're not going to use that directly in this section. So this right here is a linear differential equation. Now, at first glance, it doesn't appear to take exactly this form, but the dy dx that I'm seeing here would correspond to this y prime here, and I do have a function of x being multiplied to it. But I could just divide both sides by that function right there. So dividing everything by x squared would give me y prime here, minus, now if I divide this by x squared, I'd get an x cubed in my denominator, which I could also write as x to the negative 3 times y. And then over here, I would get x to the negative 2 cosine squared of x. So notice I have dy dx, or just y prime, same thing, plus some function of x, so that's negative x to the negative 3rd power, that's what I'm thinking of as p of x, times y equals some other function, which I'm thinking of as q of x. This is linear because this can be put into that form. This function is not linear. dy dx plus y squared equals 3x. Notice where I should be getting a function of x times y, even if that function of x is just the number 1, in which case it would look like y. The y is not just a y, I'm squaring it. So the fact that that y is being squared is what makes this a non-linear differential equation, okay? So the method that we talk about here in 9.5 is a technique for solving first-order linear differential equations only. And we need the DE to be put in this form first. So if it's not in that form yet, kind of like this DE was, you have to put it in that form before you can use this method, okay? So let's suppose that we have done that. We have a differential equation, and it's of the form dy dx plus p of xy equals q of x. If you look at the left-hand side of this differential equation, this looks a little bit like the product rule for derivatives that we learn in Calculus 1. And the reason I'm saying that is because you have two terms that are being added, just like in the product rule. One of those terms involves a function, and the other term involves the derivative of that function. Kind of like this. The v prime is kind of like the dy dx, whereas the v would be the y. Okay? What's unaccounted for is this u and this u prime here, but we have a piece of it with this p of x. So what we're going to do is we're going to multiply both sides of this equation by a new function, some unknown function, which for the time being I'm going to call mu of x. And we specifically want to figure out how to make that function such that after doing the multiplication, we get something that looks exactly like the product rule. So here's what I mean by that. Here's our original differential equation. Imagine multiplying both sides of this by some unknown function mu of x. So now I have mu of x dy dx plus mu of x p of xy equals mu of x f of x. Multiplied everything by that mu of x, okay? I want this side to look like the product rule. Now, comparing it to what we have up here, if I'm thinking of v as y, so that v prime is dy, then u is mu of x, so that u prime is mu of x p of x. That's how things would match up if I'm using the product rule. But that would imply that the derivative of mu of x is mu of x p of x. So that's this, okay? Let's see if we can use this to solve for mu. So if I treat this as an equation that I want to solve for the function mu, I can divide both sides by mu of x, so I get mu prime over mu equals what would just be p of x now. Now, because I have derivatives showing up in this equation, I can try and take an integral of both sides to solve for things. If I make a substitution, if I set u equal to mu, so that du is mu prime of x dx, then I would use that substitution to integrate this, and I would get the natural log of mu of x in absolute value. Okay, on the right-hand side, I don't know what p of x is because we're using a general function for p of x, so I'm going to leave it in that form. But I do know that once I evaluate that integral, a constant of integration is going to show up. So I'm going to just place that over here, plus c1. Now I'm going to take e to the power of both sides to eliminate the natural log. And I get the natural, or the absolute value of mu of x equals e to the power of this integral, p of x dx plus c1. As we have seen before in the previous section, using an exponent property, I can write that as e to the power of that integral times e to the power of c1. And then if I just think of that e to the c1 power as just some arbitrary constant, and then I eliminate the absolute values by putting a plus or minus on that, I can think of that plus or minus e to the c1 power as just the constant c, since it's an arbitrary constant anyways. So that means mu of x is equal to ce to the integral of p of x dx. Basically what that means is if I want this mu of x to be some function that that performs or that does what I want it to do, basically turns this into the left-hand side of the product rule right here, then any function that takes this form will do. So to keep things simple, to keep it, since I can use any function of this form to do that, let's keep it simple by setting c equal to 1, so that we just need to worry about e to the power of that integral right there. Okay, so moving on. Now that function mu that we just talked about is what's called an integrating factor, because by multiplying it to both sides of our dE, it's creating a factor that allows that thing to be integrated. So again, if I come back here, this thing is like the left-hand side of the product rule. So I can represent it by the right-hand side of the product rule, uv all prime. I'm taking the derivative of it. So by doing that, I'm showing that the derivative of u of x times y is what's appearing on the left-hand side. And now I have that set equal to the right-hand side. And now I can use integration to undo this derivative and start solving. Rather than write that out as a general process, it's more instructive to do a couple of examples. So let's start with this one. I want to solve 3 dy dx plus 12y equals 4. Okay, so remember the very first thing we need to do is make sure that this is in the form that we talked about on the previous page. It needs to be of the form dy dx with a coefficient of 1 there. And I can divide by 3 to make that happen. So that would become 4y, and this would become 4 thirds. So I divided everything by 3 because I just want that dy dx by itself. Okay. Now the next thing that we need to do is find that integrating factor mu of x. And it was defined to be e to the power of the integral of p of x dx. That's what we showed on the previous page. But if you recall, p of x is this function right here. It's the function that's acting as the coefficient on my y. So the p of x dx here is going to look like 4 dx. Okay? That's an easy integral to solve. I would get e to the 4x. Now, technically, I should be getting 4x plus a constant c here, because that's an indefinite integral. But remember, the point of this integrating factor is just to help us represent this left-hand side as the product rule, essentially. And any function of this form will do that, which means if I put a plus c here, I can plug whatever I want in for that c, any constant, and I'll get a resulting function that will do the job for me. So to keep things simple, we might as well set the plus c here equal to 0, so that I really just need e to the 4x. And we're going to do that every time we find an integrating factor. We're going to essentially ignore the plus c, because we don't need all of those antiderivatives. We just need one, and that's going to be the simplest one to use. So now what I'm going to do is go back to this form of my linear differential equation, and I'm going to multiply both sides of it by e to the 4x. So that's going to give me this, e to the 4x times dy dx plus 4e to the 4x y equals 4/3 e to the 4x, okay? And remember, the whole point of this was to make this left-hand side look like the result of the product rule. So I have y and its derivative here. I should be getting e to the 4x and its derivative here. And notice that's what I have. 4e to the 4x is the derivative of e to the 4x. So this left-hand side I can write as e to the 4x y prime, like that. Because if I took the derivative of this using the product rule, I would have ended up with this, okay? Is equal to 4/3 e to the 4x. Now, because I have a derivative here, I would like to undo that with an integral. So I'm going to put a dx there. Integral with respect to x, okay? That's just going to cancel that prime there and give me e to the 4x y equals, over here, this integral is going to become 1/3 e to the 4x. But I do need to put a plus c there this time, because we're no longer just trying to find an integrating factor. We did the work here. Now we're actually trying to find a general solution to this differential equation, and the plus c here matters for that. My only thing left to do here is solve for y. So I would be dividing both sides by e to the 4x, which gives me y equals 1/3. The e to the 4x just cancels now, plus c e to the negative 4x. That would be the solution to this thing, okay? And notice it's a family of solutions, because different values of c will give me different solutions to that dE, but they will all work. That's generally what's going to happen if we don't have an initial condition there. We have some arbitrary constant floating around in our solution. In this second problem, we do have an initial condition. So we're going to do this one next, but this time we're going to have to solve for that c that showed up at the end there using our initial condition. So same idea as before. Notice this time, this dE is already in the form that I want it to be in. Y prime plus a function of x times y equals a function of x. So in this case, that 4x right there is the thing that's acting as my p of x. So that means my integrating factor, mu of x, is equal to e to the power of the integral of that function, 4x dx, which would be equal to e to the 2x squared power. And again, remember, we don't really need the plus c there, because this is a totally usable integrating factor just as it is. So now what I want to do is multiply both sides of this dE by this, e to the 2x squared. That's going to give me e to the 2x squared y prime plus 4x e to the 2x squared y equals x cubed. I already have an e to the x squared there, and I'm multiplying it by e to the 2x squared. That's going to give me e to the 3x squared. Make sure you're using those exponent properties correctly there. The left-hand side, does it look like the product rule? Well, y will have a derivative of y prime. That means e to the 2x squared needs to have a derivative of 4x e to the 2x squared, which it does by the chain rule. So that means this thing can be written as e to the 2x squared y, all with a prime on the outside. Okay? And then I have x cubed e to the 3x squared there. Let's integrate both sides with respect to x. Okay, when I do that, the integral and the derivative simply cancel each other out. So I have e to the 2x squared times y here equals. Now this integral right here, if you look at that, it seems a little tricky to solve. So I'm going to have to do a clever u substitution to make that one work. Let's set u equal to that exponent right there. U equals 3x squared. So that du is equal to 6x dx. Now, if you're looking at it, it would be nice to have a factor of x showing up here, but I don't have that. I have an x cubed. But notice if I were to multiply these two things together, u times du, I would get 3 times 6, which is 18, x squared times x, which is x cubed, dx. By multiplying u and du, I am now getting an x cubed, which almost matches what I have here. The 18 is the only issue, but just divide both sides by 18 to resolve that issue. So that means that this integral here can be written as 1/18 times the integral of u du. Okay? Now I'm going to have e to the 2x squared y equals 1. So the derivative here is going to be, let me make sure I got the right thing. Oh, I'm missing something important, actually. I need to back this up a second. It's not just u du. If you notice, I'm missing the e to the u that should be there. So e to the u should be in there as well. Okay, so I have u e to the u. That's something that's going to require me to do integration by parts on. So integration by parts, I would set u equal to u, so that du equals du, and I would set v equal to e to the u du, so that, or dv, sorry, so that v is also just e to the u. Using my integration by parts from chapter 7, this is going to be u times v, or u times e to the u, minus the integral of v du, the integral of e to the u du. That's easy to solve. I get 1/18. Substituting 3x squared back in for my u's here, I'm going to get 3x squared e to the 3x squared minus, this integral comes out to just e to the u, so I get another e to the 3x squared there. Okay? Let's see, are we missing anything important? Oh, we are missing one kind of important thing. Once I have evaluated this integral, there should be a plus c there. So sorry for this, ignore that. That plus c is going to matter, so we need to make sure and include that. Here's what I'm going to do. I'm going to rewrite this as e to the 2x squared y equals 1/18. Let's factor the e to the 3x squared out of both of those terms. E to the 3x squared times 3x squared minus 1, but then I have that plus c in there. Okay. Finally, isolate the y by dividing both sides by e to the 2x squared. So I can divide each of these terms by that to accomplish that, and I get some simplification happening here. That's going to look like 1/18 times e to the x squared, 3x squared minus 1, plus c e to the negative 2x squared, since I divided. Okay? Now we aren't done, because I have to solve for that c there, and that's where my initial condition is going to come into play. We have y of 0 equals negative 1. So if I were to use my initial condition, I'll use this space over here for that. My y becomes negative 1 equals 1/18. Let's think about what happens if we plug a 0 in for x. So if I plug a 0 in for x, e to the 0 becomes 1. If I plug a 0 in here, I get negative 1. So 1 times negative 1 is negative 1. Plus c times e to the 0, which is also going to be 1. So I get negative 1 plus c. Okay, if I multiply both sides by 18, I'll get negative 18, and then I'm going to add that 1 over, which gives me negative 17. So C is equal to negative 17. Finally, I can write my answer. Y is equal to 1 over 18 times e to the x squared times 3x squared minus 1 plus c, that becomes minus 17 e to the negative 2x squared. This guy right here is my final answer. Okay, so we are almost done. I'm going to end this video here, but in the next one we'll do an application problem with this method for solving linear first order DEs.